extraction of metals. So using reduction using carbon. So first of all, what is oxidation and reduction? I made a video on oxidation and reduction previously, but just to summarize, oxidation in this context, because there's two meanings of oxidation. It can either mean the oxidation with air and oxidation with electrons. Anyways, for this context, we're talking about air, oxygen. So oxidation is basically the gain of oxygen, sorry. Reduction is the loss of oxygen, sorry. If we're talking about electrons, oxidation would be the reduction would be the gain of electrons, and oxidation would be the loss of electrons. With the electrons, it kind of goes against logic, and I don't even know why we use this word for electrons as well, but there's a pretty easy mnemonic to remember: oil rig. Oxidation is loss, reduction is gain. As long as you can remember that, you should be fine with oxidation and reduction in terms of electrons. But for extraction of metals, we're going to focus on this one, oxygen. Remember, oxidation is the gain of oxygen, reduction is the loss of oxygen. So why do we need to do this? Well, if we have, say, excuse me, say we have magnesium, and we're trying to get pure magnesium from the Earth. Well, magnesium is going to be on Earth, right? And on Earth, we have oxygen. By the way, oxygen is O2 because oxygen exists as a diatomic molecule. It always exists in pairs. Two oxygen atoms are together. Well, when there's magnesium and oxygen, they react together, and they oxidize to form magnesium oxide. We don't want magnesium oxide, we want pure pure magnesium, sorry. First of all, let's balance this equation. 2 oxygen here, but 1 oxygen here, so we need 2 here. 2 magnesium, but 1 here, so we need 2 there. So we just want pure magnesium, we just want this. But when you get it out of Earth, we get this. By the way, this is what we would call a oxidation reaction, because this is magnesium gaining oxygen. So when magnesium's on Earth, it's going to be in the oxidized state, and this is the process of oxidizing magnesium. What we want to do is we want to reduce the magnesium. Remember, reducing is the reduction, so the removal of oxygen. So when we find magnesium in its natural state, we're going to get magnesium oxide, right? And it's going to be 2 because we need the equation to be balanced. We want to get it into pure magnesium and just oxygen. Let's just balance this equation out. 2 magnesiums here, so we need 2 here, and oxygen is 2, 2. Yeah. So we just want this pure magnesium. And this is called a reduction reaction, when you remove the oxygen. How do you do that? So first of all, why does this happen? Most metals are reactive, right? Excluding like gold, which is like super unreactive. Pretty much every metal except gold reacts with oxygen to form a metal oxide. We don't want a metal oxide, we just want the metal, right? So they oxidize into a metal oxide because it reacts with oxygen, except gold, because gold being gold is unreactive. That's probably why it's expensive too. Another example, iron gets oxidized with oxygen to form iron oxide. This iron oxide is what we commonly call rust. So this iron has been oxidized. We want this gone, so we need to reduce it. So because oxygen is so common in our atmosphere, O2 is very common. It's basically everywhere, right? We need it to breathe too. As long as the metal is reactive enough, for example, anything but gold, and left long enough, it will most likely have been oxidized. Most metals are oxidized as long as they're reactive enough, i.e. not gold. So when metals bond with other elements, metals can bond with other elements too, but oxygen, like metals bonding with oxygen, is by far the most common example. And for your GCSEs, what you need to know is how we can remove and get rid of this oxygen in the metal oxide. We don't want the metal oxide, right? So we need to learn how to remove this oxygen and how you can just get pure metal. which we will look at now. So how do we do that? We can do something called reducing with carbon. So reduction with carbon. Remember, reduction means removing the oxygen. Reduction with carbon. So reducing the metal oxides to get pure metals. So you react the metal oxide with carbon. Okay? So basically what would happen is, if we write an equation, metal oxide, it's a generic equation for any metal oxides. The metal oxide reacts with the carbon to go and form pure metal, which we want, and we also get carbon dioxide. You already noticed that the carbon just started as C, right? It's going to receive the oxygen from the metal oxide, leaving this metal alone, pure metal, and the oxygen goes into the carbon to give carbon dioxide. You see notice the oxygen there? Right? So the oxygen is taken from the metal oxide and given to carbon, leaving behind a pure metal. Take a look at another example. If we have copper oxide reacting with carbon, it's going to go form copper, pure copper, and carbon dioxide. Let's balance out the equation. We have one carbon here and one carbon here. Carbon's fine. One copper here, one copper here. Copper's fine. One oxygen here, but two oxygens here. So we need to balance it. 2. Now we have 2 coppers here and then 1 copper here. So we need to balance it. 2. And then everything else is balanced. So the copper oxide reacts together with carbon to form pure copper and CO2, carbon dioxide. Basically, the oxygen is basically just transferred over to the carbon. However, like always, there's always a catch to this reduction with carbon method. Metal has to be less reactive than carbon. This is the catch. The metal just always has to be less reactive than the carbon. And this is also why we include in our reactivity series, we include carbon in it, because that's why we know if the metal is more reactive or less reactive, so that we can know if we can use reduction with carbon method. So this reduction method using carbon, so it can only be used for metals that are below carbon in the reactivity series. So if you look at your reactivity series, you'll notice we have, let me insert a text box actually, that'll make it a lot clearer. We have potassium, sodium. So these are the elements in the reactivity series that you need to know for your GCSEs. Potassium, sodium, lithium, calcium, magnesium, aluminum, and we have carbon. I'll write that in bold. Carbon, that's the non-metal, just for comparison. And we have zinc, iron, hydrogen, also for comparison, copper, silver, and gold. Right? Let me put this in red, just so you can see it a bit more clearly. So, by the way, this is the reactivity series for your IGCSEs. If you're doing normal GCSEs, you don't need to know all of these. For example, you don't need to know silver and gold in your reactivity series, but it is useful to know. But at least if you're doing normal GCSE, you don't need to know silver and gold. But anyways, so carbon is here. So for anything below carbon, we can use the reduction with carbon method. Reduction with carbon. So we can react the elements with carbon, and because they're less reactive, carbon will be able to take the oxygen away from them. This is kind of like the displacement reaction. Remember displacement reactions? Not sure if you guys would remember that. Basically, if we have a more reactive metal, so higher up in the reactivity series, with a less reactive metal, watch my video on the displacement reactions if you don't know this, and you have a less reactive metal bonded with another compound, the more reactive metal can steal the compound away. So it becomes more reactive. This is a really brief explanation, summary, by the way. it becomes more reactive plus compound, and just the less reactive is left alone. Basically what happens is the more reactive metal steals away the money from the less reactive ones, and it becomes the more reactive one with the money, and the less reactive one is left with nothing. It's kind of the same with carbon. Notice here, the carbon, because it's more reactive than the copper, it steals the oxygen away and leaves copper alone. You can imagine it like that. Pretty easy if you understand that way. That's why it needs to be lower than carbon in the reactivity series, so that it can steal. Don't write this on your exams, by the way, but so that it can steal the oxygen away and reduce it into just pure metal, right? But anytime it's more reactive than carbon, for example, all these, you cannot use the reduction with carbon method because carbon is less reactive, so it can't steal the oxygen away. So what would you use for that? You would do something called electrolysis. Electrolysis is when you use like a bunch of energy to separate out the different atoms. That's another video for another day. But anyways, that's what you need to know. If it's below carbon and you want to separate the metal oxide into just pure metal, you can reduce it using carbon. Let's take a look at one more example. This is an example that you have to know for your GCSEs. It's mining for iron. All right? Mining for iron. So in Earth, we'll have a bunch of rocks, and in here, you might have some parts of it being iron. So you would separate out the parts that include iron, and you get something called iron ores. What are iron ores? Ores are basically just metal-rich compounds. Metal-rich compounds that we can use to extract metal from. Right? And then in this metal-rich compound, iron ore, we will get Fe2O3, also commonly known as rust. So this is the metal oxide. In this case, it's the iron oxide, because we were talking about iron. Well, the iron, Fe, is super reactive. It's not super reactive, but if you look at the reactivity series, iron is here. And iron can react with oxygen. We know that because we form rust. Rust is the most common example that we always know. So iron will react with oxygen to form Fe2O3. We could balance that out later. That's not really important for now. Thing is, we don't want this metal oxide. We don't want this iron oxide. We want to get rid of it. We just want pure metal, pure iron. So what would we do to get rid of the Fe2O3 that we find on Earth, the metal oxide? We can reduce it using carbon because carbon is less reactive. So in your exams, you'll say carbon is more reactive than iron. So we can reduce with carbon to remove the oxygen in iron oxide, right? What would this look like in an equation? We get Fe2O3. This will be reduced into pure iron and carbon dioxide. Let's balance the equation out. Well, we have 1 iron here and 2 iron here, so we need 2 iron here. And we have 3 oxygens here, but just 2 oxygens here. So what we do? Well, we're going to multiply this out by 2. Yeah. Basically, balancing equations is basically just try and error. We have 6 oxygens here now, so we can multiply this by 3 to get 6 oxygens here. So the oxygens are balanced. We have 3 carbons here, and oh yeah, I forgot one really important part. What am I doing? So sorry, guys. I forgot to say that we react the iron oxide. I'm gonna run out of space if I do it that way. Reacts with the carbon. So we have the 6 oxygens, 6 oxygens. The oxygens are balanced. 3 carbons, 1 carbon. Well, let's put 3 carbons here then. The carbons are balanced. 2 irons, 4 irons. Well, that's not going to be balanced. Let's change that to 4. Is everything balanced? 4 irons, 4 irons. 3 carbons, 3 carbons, 6 oxygens, and 6 oxygens. Yes, now it's balanced. What we did is we reduce the Fe2O3, the iron, the rust, iron oxide, to get pure iron and carbon dioxide. and we've reduced it by using carbon. That's all you have to know for reducing metals using carbon. And remember, when the metal is more reactive than the carbon, we can't use this method because carbon won't be able to steal the oxygen away. You'll have to use something called electrolysis. We can still use electrolysis for these, but electrolysis is much like carbon. The reduction using carbon is much more preferred because it's way cheaper. Electrolysis is expensive. You need a ton of energy.